Good morning, good afternoon, good evening, everyone here in person and in the virtual room. This talk is about evaluating the security posture of graph neural network models. The main contributor is Dr. Zhang and his research group from CISPA, Germany. For the past decades, we have seen many successful machine learning models ranging from facial recognition to voice recognition and to the latest large-scale language models and text-to-image generators. But today, we're going to stay away from the images and text, audio, video. We're going to talk about graph. Graph, they are everywhere. This is not an unfamiliar concept. They have arbitrary sizes, and the examples are plenty. Social graph, knowledge graphs, your purchase history, like the user item interaction graphs, even the molecular, they can be represented as molecular graphs. And the applications, they're also everywhere as well. You go on the e-commerce website, they have the recommendation for you. We found the item you may be interested. And you go on the social network, they will actually tell you that, do you know someone? You want to connect it with him or her? All sorts of the things. And recently, there is a new trend for the drug e-discovery. So instead of looking at the toxicities of the molecules in the lab, you can use the graph neural network to do the toxicity prediction. So this pretty much pervasive, the graph applications. And the traditional deep neural networks, they have been proven pretty much successful for the past decades, but they're designed for grids like images or sequences for text. In light of the success, graph neural network was invented back in 2014-15. Basically, the goal is to map an input graph, like the graph is not readily consumable by our computers, into the Euclidean space, into vectors. So that in that case, you can start consuming that in the computers. To do that, there's a technology called the messaging passing used by graph neural network. So basically, they just aggregate your labels information in a recursive way. And based on the different technologies, you have different aggregators such as graph convolutional network or graph isomorphism networks. And once you map the node into the Euclidean space, you can start doing the node classification, link prediction based on the distance between the vectors. And if we go further into the graph level, you will actually have one thing is the core concept of graph level mapping is you have the node embeddings, you have a graph, you have k nodes, and you want to compress them into a single vector. So the entire graph is represented by a single vector. If you do that, you can go there and do the graph classification and matching and visualization. You can also do the toxicity prediction, as I mentioned before. So these are the applications and the graph levels, just some background. And all these big companies, you name it, Google, Twitter, and the different applications, they are all doing this graph neural network. I mean, it is pretty much invisible, but this in the background, in the back end, to support your daily life. And yes, when we are talking about the bright side of machine learning, here comes the dark side. Let's talk about the adversarial machine learning. If you do that in the Google News, you probably see all the screenshots I'm doing here. This is a big topic recently. It's about the security of the machine learning models themselves. We pretty much agree with the Air Force magazine. It's like, does AI represent the attack surface for the adversaries? So let's talk about if the graph neural network is actually a new attack surface. I will talk about the 4 attacks, and I will start with the link re-identification attack. The goal of this attack is to identify if 2 nodes are connected in the private data. Right. Here is actually the scenario. We frame our graph neural network in the node classification task. And the attacker's capability is that they can be able to breach where you store your posterior scores. Why it is a valid scenario? Let us take this gigantic social network, for example. You pump that into the graph neural network. You take your CPU hours, and you generate posteriors of each node. And you don't do that very frequently, so you store in the database. Upon the adversary breach this database where you store the results, they can start inferring if two nodes are actually connected in your private graph. You don't want to disclose that information. Just put that into the contact tracing framework, right? You don't want to disclose that if two patients are connected together. There's too much private information there. How do they do that? So this is actually, we talk about the link re-identification attack. So upon they get the posterior scores, they are literally just two vectors, right? Just simplify the example here. They can immediately just use the posterior similarity to calculate that. If it is greater than a threshold, there is a link exists between these two nodes, otherwise not. Even we take this very straightforward approach, the performance is reasonably okay, but not really good. Then we think about the second scenario. Since the attackers already know that this posterior score are generated by a graph neural network model, how about I use a shadow data set and build the model by myself? Then here's what they can do. I have to stress, they do that in their local environment. There is no interaction with the remote model they're targeting. What they do is that they have the shadow model, they have the shadow data set. They will build their own shadow model, still as a graph neural network. From there, they will get the posterior scores of all the nodes, because they actually control the whole environment. They can create a MLP as their attack model. For example, they can use the concatenation of these two posterior scores together and train with the positive and negative edges. Once they do that, okay, they'll be pretty much as it is. Take this one, for example. If the posterior scores, they are actually 4. If they contact them together, you will get a dimension 8 vector. Suppose the database you breach is actually returning you a length 3 vectors. Contacting them together, that means a dimension of 6. So there is a dimension mismatch. You cannot just easily do that. A simple solution, just goes through what we tried, is to unify the input of this attack model. So we have a different distance functions to unify the posterior score. At the same time, we use 4 different entropies to calculate the difference between the posterior scores that we are supposed to train. Then we build this attack model. And once you breach the database, you can see that you have the unified input, then your model works. Performance-wise, it increases the previous simple solution, like just directly calculating the similarity between the posterior scores. And one important thing you're looking at here is like you don't necessarily need to use the same data set the target model is training. For example, you can use a CiteSeer, it's a citation graph. It can actually improve the link re-identification from the protein data set. From there, we just switch the gear. We talk about the posterior scores. What if the attackers actually get the graph embeddings from your environment? Here, I put these two together. It'll be easier to see the values or the consequence of these two attacks together. The first one is property inference attack. So basically, the attacker can actually infer the basic graph properties from a graph embedding. The second one is they can actually infer if a certain subgraph exists in a graph via its graph embedding. I'll start with this one, just a quick recap, graph embedding. Just bear in mind, the entire graph is represented by a single vector. Just a quick recap of this before we move forward. And here's a scenario. We frame the graph neural network model's task is graph classification. And the attacker capability is, first, they breach your database, they get the graph embeddings. Second, they can query the graph neural network model. So this is the difference between the property inference attack and link re-identity attack. And just a bit background, it's like you have this private graphs database, you pump them into a graph neural network, and you get the graph embeddings. For the graph embedding, you don't necessarily need to do that every time unless you have a new graph neural network model. So it is pretty much like a natural process to do that only once and store in the database. Upon the attacker actually breach the database, what can they do, right? Because you will think that they are just vectors. There probably won't be that much harm. And the first one they can do is to infer from this vector that this is actually a graph with approximately 4 nodes, just for example. How do they achieve this goal? First, the attackers, they have to have their own auxiliary graphs. If we frame that into the molecular graph environment, right? Suppose you do the molecular toxicity prediction, it's easy for them to obtain a set of these auxiliary molecular graphs. They just query the graph neural network model and get the response like the graph embeddings. So from there on, they will build the attack model locally. I have to stress, they do that. Once they get the graph embeddings, there is no further interaction with the target model. They just build a MLP model, literally, like the attack model. They can use the estimated number of nodes with the ground truth because they already control the auxiliary graph. So for example, they already know that the first auxiliary graph has 4 nodes, and the second one actually have 5 nodes. So they put into the different buckets. They will help them to roughly estimate the size of the graph. And upon doing that, they train their attack model. They just pump the graph embeddings they breached into this attack model. They can successfully estimate the number of nodes from this graph. And the performance-wise, it is okay-ish. We use 5 publicly used bunch data set. For example, if we take the enzymes, for example, the very first row, the second figure, you can see that the attacker, if the fine granularity information cannot be inferred, but they can actually infer a reasonably like rough size of this graph. But it doesn't add much value to the attackers. So here's a graph I estimated is actually there are 4 nodes. There's not much I can get. However, there is one further attack we talk about is the subgraph inference attack. The attacker can infer if this graph contains a specific subgraph. For example, here, a triangle. Recall that we can estimate the size of the graph, adding them together. It will further reduce the search space of the attacker to reconstruct your graph. If we further frame that into the molecular graph concept, it's like if you have this $1 million molecular graph, right? And the attacker just gets this embedding, they can actually just infer if they have a specific subgraph in this molecular graph. Then by estimating the size of the graph, they can gradually just reduce their search size to replicate your molecular graph, right? That's the impact of this attack. How do they do that? It's the same thing. The attackers still have to have the auxiliary graphs. They talk to query the remote graph neural network model and get the graph embeddings out. The special treatment they have to do is have to build a local model. And this local model, the only functionality is to generate the subgraph embeddings you are interested with, right? I've stressed this is actually a local model. And then they combine the graph embeddings, they queried with this subgraph embeddings, and they can generate the negative pair because they know that this triangle does not exist in the auxiliary graph, the top one. And also they can generate the positive pairs because they know that the triangle exists in the auxiliary graph, number 2, and so on and so forth. Once they do that, they can just build an AMP model, literally just converting this one into a binary classification problem. Same thing, like once they get the graph embeddings from your database, they can start getting the subgraph embedding, combine them together, pump into the attack model, and give you an estimation whether this embedding contains a triangle or not. Our evaluation shows that the best way to combine these two things together is to use the graph embedding difference, like using the difference between graph embeddings and subgraph embeddings to train the attack model. The performance, look at the ORC score is probably between 0.6 to 0.85 or something like that, but it's reasonably good. If we just switch the brick a bit, we look at these attacks we already covered. Basically, the basic foundation is like the attacker can actually breach your database, right? If you secure your database, all these things that you store in your environment, you can pretty much prevent these two attacks from happening, right? Because they don't have the embeddings, they don't have the posterior scores, they cannot carry out these attacks. So here comes the takeaway part one, is secure your infrastructure, and also at the same time audit your graph neural network-based machine learning pipeline. You may have heard of these recommendations, but the machine learning model, don't take a cavalier attitude towards this graph neural network model. Their output has meaningful information inside. So they're not just numbers. What's next? You secure your database, you prevent the link re-identification attack, property inference attack, subgraph inference attack. What can they do? So along the pipeline, the model itself. You spend the money to connect your data, you spend the money to build the graph neural network model, and the model itself is really valuable, right? Normally, you just open up this model and serve the customers. That's probably you're gonna do. That's where we're gonna talk about with the model extraction attack, is the attacker is gonna faithfully replicate the model's functionality remotely, and they don't wanna breach your security boundary as well. Let's talk about the details. So you have this model, you build it, you train it, and you offer the response to the customers, and you secure your infrastructure, you take all the advice we just mentioned, and you open up to the customer, you provide a secure API, so the customer can query the graph neural network model and get a response from the model and build their downstream applications. Everything is fine. However, if you look at from the attacker perspective, they can pretend to be your customer, they pay for your subscription, they still go to the secure API. There's nothing you can detect here because they're customers. Their goal is to get the response, and the response replicate the functionality of your model. And the whole process works like this. Don't be scared by this workflow. I will expand to them one by one. I will start with learning the discrete graph structure. It is pretty straightforward. If the attackers, they already have the graph, they can just do the query to the target model, then they can just get the response. But potentially, they may actually not have the graph structure. Suppose that they only have the user profile, but they don't have the connection between the users. What they have to do is to build a graph. I mean, some structure is there, and to query the target model. We use the IDGO framework to learn the discrete graph structure. I will not go into the details. You have the reference. And in the worst case, if you don't have this framework in your system, the attacker can actually just use the GNN algorithm to have a bare minimum structure and query the target model. That's the step one. They just have to build a graph somewhere from the data that they have. Upon they actually have the graph structure, they will have to make the full use of the response from the target model. We actually talk about 3 scenarios. The target model can return load embeddings, they can return the posterior scores, or they can just return the t-SNE projection scores. I mean, t-SNE is a popular data visualization framework. They just project the high dimension data into 3D or 2D space. You can just visualize them easily. How do they do that? Back to the query graph. They just pump this query graph to the target model, and the target model gonna send the response back. And recall that what we have talked about before is they're gonna return you the vectors, right? Regardless it's embedding or prediction or t-SNE projection. They're just float number vectors. You map them into the Euclidean space, probably something look like this. At the same time, the same query graph gonna be pumping to the attacker's surrogate model, and they will get the response from the surrogate model as well. They may not, let's say, they're not matching each other at the moment. The attacker's goal, the first goal, is to make sure that they use this first loss function to move the triangle close to the squares. The foundation of this loss function is to maintain the similar spatial connectivity in the Euclidean space between the surrogate model and the target model. Once they do that, the second goal they want to achieve is the classification, because we frame that this attack is in the load classification task. Suppose that these two nodes, they have different classes, and from the target model perspective, they have different decision boundaries. The attacker just need to make sure that these triangles, they are put into the same boundary with the same classes. That's why we use a cross-entropy loss as the second step to push this, to make sure that the surrogate model gonna make the same decision as the target model does. All right. Now, talking about the results. So the results is quite fascinating. Is the first thing is like the attacker, they can conduct the attack with a low in the target model's architecture. All they need to know is that the target model is using the graph neural network models, right? So they can just have different surrogate models such as graph convolution network, or they can use the graph isomorphism network, as long as the project, just mimicking the behavior of the target model. So everything's gonna be the triangle and the squares, they're gonna be pushed together, right? So that's the core goal of the attacker. And the evaluation results shows that the attacker can only use about 3% of the target model's training data. Like, so for example, if you use 100K, the size of the training data set is 100K nodes, the attacker only need to use 3K queries to replicate the performance of your target, of your model. Our evaluation shows that here you can see that, suppose that the target model is built by Graph Sage, and the attacker actually use the GNN, which is graph isomorphism network, to replicate your functionality, just like about 2% difference in terms of the prediction accuracy. The second thing that we found out is the two-dimensional t-SNE projection can be the new attack surface. This is pretty scary because the t-SNE projection we test is a two-dimensional one. That means one node will be represented by two coordinates, right? You just project that, like this square or triangle. It has bare minimum information in these vectors, just as we projected. But it's not the case. We evaluate that. We show that, yes, there is a performance drop because you only have the node is represented by two float numbers. But still, the attacker can actually replicate the functionality with reasonably good performance. So for example, if you look at the target model as GAT, the graph attention network, and the surrogate model is GEN, again, the difference is about 40%, right? It is a big drop. But if you look at the target model as the GEN and the surrogate model as Graph Sage, the performance drop is only 7%. That means the attacker can really replicate certain functionalities out of your model. That's pretty much the information I want to pass on here. What can we do for the defense? The Defense is a tricky one. The usual approach is to add perturbation, like add some random noise to your response. So for example, here, if you use the Gaussian noise, right? So these squares are gonna be randomly pushed somewhere else rather than the original position, it be pushed somewhere else. However, if you look at the first loss function, the core functionality of this loss is to make sure that whatever you have project into the Euclidean space will be tracked by the attacker model. So in this case, you won't be able to staying away from just by perturbation. You won't be able to, like say, reduce the attack. Our evaluation shows that the t-SNE, let's say, take these two figures, for example, both t-SNE and embedding. Embedding contains the most information, and t-SNE contains least information in terms of the target model's response. And the delta is the standard deviation of the Gaussian noise. We vary that noise and show that the attacker can still pretty much just like track your target model and still return a reasonable performance. So I mean, we put this one as a future research direction to see how we can figure out a way, like without reducing the functionality of your model, and at the same time, the attacker cannot replicate the functionality of your target model, right? So here comes the takeaway part 2. The first thing is monitor your model logs for anomalies. The one thing that you can look into is to understand the customer, if they actually send some strange queries to your system, because you will see if you're a legit customer, maybe at the beginning, they will send you the graphs and the predictions may fluctuate a little bit. But as a mature customer, if they suddenly send you some information and you notice that the performance drops for no reason, and for the other customers, the performance still pretty good, that means something is off. You probably have to keep an eye on your logs for that kind of customers, figure out what kind of data they pump into your system. And the second thing is to evaluate the security and the privacy posture of your graph neural network models. Personally speaking, I would go as far as pen testing your graph neural network models. This represents a new attack surface. Like, take this previous example, for example, like this model extraction. You have your secure boundary, you have your secure API, everything is by book secure, but still, your model can be replicated by the attackers. That's pretty scary. That means you have to seriously figure out different ways to pen test your model's security posture and understand what will be the consequence by exposing your model to the customers and what kind of defense mechanism you can apply to the model to make sure that everything is fine and your functionalities will not be replicated by the attackers. I mean, to facilitate the community, we release the code. They are all open sourced. You can feel free to grab the source code and adapt to your framework or environment to understand to what extent your system is exposed to the different attacks. And for that, I conclude my presentation. I'm ready to take questions. The privacy posture, it's pretty hard to, let me just go back to the pipeline here. The privacy things that you can do, the first thing talk about that auditing the graph neural network learning pipeline. The first thing you can do is to make sure that your training graph is not accessed by unauthorized personnel. That's the first thing. The second thing is like, don't expose the posteriors to unauthorized person as well. So in that case, they don't have the original posterior scores embeddings of your training data. The key message is like the raw training graph, they are private for sure. But the transformed vectors of the training data is also, I mean, let's say, it's still quite sensitive, the private information. So you have to secure both the raw data and the transformed data.
Please head to the microphone to give your questions, please. It's in the middle aisle. Thank you.
Can you talk a bit more about size and scale with very large models coming up these days? Do you think these kinds of attacks and defenses apply equally to billion parameter models or 100 billion parameter models?
Can you repeat your question again?
Can you talk a bit about if this changes with scale? So we have very large parameter models flying around doing cool things in the first few slides of your presentation. Does some of the techniques you talked about change when you're going beyond 100K node training sets and into much larger models?
So your question is like, if the training data is big, can the function still be replicated by the queries?
Yeah.
That's a good question. I mean, let's just take this functionality, for example, if you take the social network, right? Social network always reaches tens of millions. The first thing that you get your model gonna be quite complicated. To understand the decision boundary, that probably is easier for me just go down to the decision boundary here. Just give me 1 second here. So the decision boundary can be complicated. I have to say it is really complex. One thing that you can, I mean, from the attacker perspective, they can pump into slightly larger query data to understand to what extent, I mean, just for example, in this Euclidean space, right, you pump into your query and you can always understand the decision boundaries of your query data, right? That is one thing that you can do. And from there, you can just fine-tune your queries to certain perspectives. So for example, you vary your load features, the decision boundary can change or not change. So you will be able to understand if the node features, I mean, the graph neural network is sensitive to the node features or is actually sensitive to the graph structure. You will be able to understand that. And to answer your question, without exception, the attackers, they have to pump into more data to understand the decision boundary. If your data is reached tens of billions, I would say the attacker has to stay with your customer as your customer for at least a couple months to cover up their trace, and hopefully they will be able to replace your model's functionality. But still, it is possible.
You mentioned
5 minutes, Professor Zhang.
You mentioned about 3% of the size of an attacker before. Do you think that changes with scale? Say to like, if you were trying to replicate a billion model of Facebook?
For that, we haven't done any large-scale test, because for our test is reaching about, let's say, 20, I mean, not 20-ish. It is probably between 100K and 20K. We reached that scale, it is 3%. We envision that for graphs, there is a property called associativity in the classic graph theory. It's like the nodes that share similar features, they're gonna be close in the graph. So in that case, maybe if you use a social network, let's say the size is still big, like tens of millions, but your decision boundary can be quite straightforward because you have a cluster of data that group together. So for example, you have people that they are interested into black hat, right? They're probably gonna be connected to each other like a very close, like this complete graph, almost quite dense graph. And from the decision boundary perspective, once they map into the Euclidean space, the nodes are going to be close to each other, like almost a cluster. So in that case, your decision boundary is quite straightforward. And the attacker can still use reasonably less data to query your model and get the functionality replicated. I mean, again, we require large-scale tests.